So in this PowerPoint, over sections 22.4 and 22.5, I'm going to talk a little bit more about how our body digests carbohydrates. So we're first going to think about carbohydrates in large terms, the kinds of carbohydrates that we ingest with our food. And then we're going to talk specifically about breaking down a glucose molecule and how the cells do that to acquire high energy molecules like ATP. So in this particular section, we've got most of the carbohydrates are depicted as these blue hexagons. And I just want to remind you guys that when you see this kind of stretch of what are represented as glucose molecules tacked together, what you really have is this alpha 1 to 4 linkage for each of these glucose molecules. So each linkage from one glucose to the next is an alpha 1 to 4 glycosidic bond. And it's those bonds that we'll be breaking to make individual glucose molecules that our body can ingest. So just to remind you guys that digestion of carbohydrates begins with the saliva in our mouths, and there's an enzyme called amylase that's present that's emitted with our saliva that actually starts the process of breaking down polysaccharides. And they're going to break those polysaccharides down into molecules like maltose. Remember that maltose is a disaccharide where two glucose molecules are linked together, and some individual glucose molecules. Now the rest of the digestion of carbohydrates is going to happen in the small intestine, where an analogous enzyme that's secreted by the pancreas will actually serve to continue to digest the starches or the polysaccharides that we eat. Now in this case, we're going to continue to break down our molecules into individual monosaccharides, where maltose, lactose, and sucrose are all going to be broken down into their individual monosaccharide components. So most of those monosaccharides are going to be in the form of glucose, which is going to be directly transported into the blood through the intestinal cells that line our small intestine. So we start out in the mouth breaking molecules down. So dextrin is a term that we use for multiple glucose molecules tacked together. If it's down to a disaccharide, that's called maltose. And of course, individual glucose molecules are what will eventually be absorbed by the intestines. Now, lactose is another sugar that we can digest or that we can ingest with our food. And remember that lactose and sucrose are disaccharides that contain one unit of glucose, but then one unit of another sugar. So lactose will yield individual galactose molecules, and sucrose will yield individual fructose molecules. Now, both of these can very easily be converted into glucose. So people that are lactose intolerant tend to be unable to synthesize this enzyme called lactase. Lactase is the enzyme that basically cuts our lactose molecule into the two individual components. So people that are lactose intolerant can very often take enzymes prior to ingesting dairy products that will allow them to break this molecule down into the individual monosaccharides. So once we've got those monosaccharides, most of those are going to be converted into glucose. So remember that lactose and fructose are only very minimally different from glucose. And so both of them can be readily converted into glucose. Glucose then is going to be the primary molecule that is used to provide energy for lots of different cells of our body. Now the breakdown of glucose begins with the process we call glycolysis. So in glycolysis, we're going to take our 6-carbon glucose molecule and oxidize it. We're breaking it down from a large molecule into smaller molecules. As we do that, we're going to ultimately generate high energy molecules. Now to start off, we have to invest a couple of ATPs, and then from that we will generate NADH and as well as ADP. At the end of that, we're going to have 3 carbon units that will then continue to be oxidized in another metabolic pathway that we're going to talk about a little later. So glycolysis is the metabolic pathway that uses glucose as its primary substrate. So we break polysaccharides down into monosaccharides. Monosaccharides can then be converted into glucose if they aren't glucose already. So we're going to take that 6-carbon sugar, break it down into 3 carbon molecules. The final product of glycolysis is pyruvate. So for every 1 glucose molecule, you generate 2 pyruvate molecules. Now this process does not directly require the presence of oxygen. However, if we get all the energy that we can out of glucose, that will require oxygen. So glycolysis itself is an anaerobic process. Every living cell that has been studied, as far as I know, has the capacity to undergo the process of glycolysis. Everybody can use glucose as a way to get at least a small amount of energy. Now again, we're going to start out this process of using glucose by investing a little bit of energy. Now the investment is going to be pretty minimal compared to the long-term return that we're going to get if we can break that glucose molecule all the way down into carbon dioxide and water. Remember that carbon dioxide and water were used to make the glucose molecule in a plant cell. And now we are going to take that glucose molecule, the cells of our body are going to break that down and generate or use that to generate high energy molecules. However, to start that off, we have 2 early steps in the pathway that are going to require the use of ATP. And we're going to look at these in very specific detail. So we're starting out with a glucose molecule. The glucose molecule is the same molecule that you have learned how to draw in chapter 15. Now there's an enzyme in our cells called hexokinase. Now enzyme names will always reflect what they do as a job. Any name that has the term, or any enzyme name that contains kinase, suggests that that enzyme is going to be involved in the phosphorylation of something. Now the other part of the name is going to be hexo. The hexo part of the name is reflecting the substrate. Remember that glucose is a 6-carbon molecule. Carbon 1 is right here, so carbon 1, carbon 2, 3, 4, 5, and 6. So glucose is a hexose. So hexokinase is going to utilize an ATP to add a phosphate group onto the oxygen at carbon 6. So that changes the chemistry of our molecule, and therefore we change the name. It's now called glucose 6-phosphate. The only difference is that a phosphate group is attached to the oxygen at carbon 6. Now the reason that I have an asterisk here by hexokinase is because hexokinase is one of 3 steps that will be very highly regulated. In other words, the use of the pathway and whether the pathway is turned on to use glucose or turned off to not use glucose is going to be controlled by 3 enzymes, and hexokinase is the first of those 3. Now the next change that occurs is going to be a rearrangement of atoms. We're going to be going from glucose 6-phosphate to fructose 6-phosphate. So remember that the difference between glucose and fructose is that the double bond O in glucose is at carbon 1, and in fructose, the double bond O is at carbon 2. So what that's going to mean is that our O link between carbon 5 is going to change from being linked to carbon 1 of glucose to being linked to carbon 2 of fructose. So this is going to be carbon 1 of our fructose molecule. This is carbon 2, and then 3, 4, 5, and 6. So here's our 6 with our phosphate on there. So fructose 6-phosphate is the name of that molecule. And that's going to be carried out by an enzyme that is called isomerase. So isomerase represents the fact that it's rearranging where the carbon double bond O would have been located in our 2 molecules. Now, glucose 6-phosphate is then converted into glucose 1,6-bisphosphate. Now, what the enzyme is doing, the enzyme is phosphofructokinase. So the kinase part of the name is telling us that we're going to be adding on a phosphate, which we do. We add that on to carbon 1. So right here at carbon 1, we're adding on a phosphate. And phosphofructo is representing the substrate. So it's a phosphorylated version of fructose. So the fructose 6-phosphate is the substrate. We consume an ATP to add a phosphate on to the OH of carbon 1. That's going to give us fructose 1,6-bisphosphate. We call it bisphosphate and not diphosphate because the two phosphates are on different locations. So here is one phosphate, here is the other phosphate. The diphosphate, as in adenine diphosphate, the molecule ADP, those two phosphates are connected together. So when you see a diphosphate, it's two phosphates linked together directly. When you see a bisphosphate, that means two phosphates but on different atoms. Okay, so fructose 1,6-bisphosphate. Now this is the second regulated enzyme, and this is the most highly regulated enzyme. This is really the major control point of the glycolytic pathway. So this is the major on-off switch, and there's lots of information that feeds in to this enzyme to tell the enzyme whether or not to be turned on or turned off. When it's turned on, it's going to phosphorylate fructose 6-phosphate and give us fructose 1,6-bisphosphate. Now at this point, our 6-carbon molecule is cut in half, and that's carried out by an enzyme called aldolase. So there are two different products. They're going to have a different location for the C double bond O. One of them is called dihydroxyacetone phosphate, and one is called glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate is the only molecule that can continue on. So dihydroxyacetone phosphate, or DHAP, is converted very quickly by an isomerase into glyceraldehyde 3-phosphate. So it's going to convert our C double bond O from this carbon to the carbon not containing the phosphate. Now that summarizes the energy investment part of glycolysis, and then we enter into the energy producing part. So this is where we generate 4 ATP molecules in addition to some NADH molecules. So we start out with glyceraldehyde 3-phosphate. This is basically a molecule with one phosphate group on it. And the enzyme, glyceraldehyde 3-phosphate dehydrogenase, is going to add a second phosphate onto that. So it's going to use an inorganic phosphate, so a free floating phosphate group, and it's going to create, along with that, it's going to create a high energy NADH molecule. So it's going to take away this H right here, add it to NAD, along with the electrons that go along with it, and we're adding on a phosphate, which is going to be linked to the carbon through an oxygen. And the oxygen came along with this phosphate. The phosphate is really a phosphorus with 4 oxygens all around it, and so that's where this oxygen link comes in. The molecule that's generated then is 1,6-bisphosphoglycerate. So 2 phosphates is indicated by the bis-phospho part, and it's glycerate because of the 3-carbon backbone. We then very quickly, from this high energy molecule, can make another ATP molecule through a kinase. So remember, kinases are going to deal with ATPs and phosphates. So the first phosphate that we just added on can now be removed and used to generate an ATP. That's going to give us 3-phosphoglycerate. So we've lost the phosphate at 1, and therefore no longer need the bis nor the 1, but we have it continue to be phosphorylated at at the OH on carbon 3. So 3-phosphoglycerate is the name here. That 3-phosphoglycerate is going to be rearranged. So when you see an enzyme with the term mutase, a mutase is basically taking a phosphate and changing its location. So this location is being changed from position 3 to position 2, and therefore the name is converted from 3-phosphoglycerate to 2-phosphoglycerate. The 2-phosphoglycerate is then going to be converted into a very high energy molecule called phosphoenol pyruvate. And this enzyme's name is enolase. Again, it's going to take out a water. It's going to form a double bond right here between carbon 2 and carbon 3. And then this is a very, very high energy molecule. And this molecule can then be used directly to phosphorylate ATP, or to phosphorylate ADP to create ATP. And that enzyme is called pyruvate kinase. It's a kinase, again, because it's dealing with a phosphate group that's now being transferred to make ATP. And that gives us the final product of pyruvate. So again, pyruvate is the end product of our glycolysis process. We've taken a 6-carbon glucose molecule, we've converted it into 2 3-carbon glyceraldehyde 3-phosphate molecules. So this process will happen 2 times for every glucose molecule to yield 2 pyruvate molecules for every glucose molecule that we utilize in this process. So pyruvate kinase is the third and final highly regulated enzyme that, again, is going to be a control point in the process. So if there's a large accumulation of pyruvate, then pyruvate kinase will be turned off and will accumulate a little bit of phosphoenol pyruvate. So that takes us through the first part of breaking glucose down into smaller products and generating high energy molecules. Now, the rest of the process is going to utilize pyruvate. We'll talk about pyruvate more in one of the other recorded lectures in a little bit. So glycolysis, if you want to sum it up, we require 2 ATPs to get us started to make our glucose molecule into glucose 6-phosphate. We then have to rearrange that molecule to give us fructose 6-phosphate. And then once we get to this point, we phosphorylate it again, and then ultimately we generate 4 ATPs and 2 NADH for every glucose molecule. So the net gain of ATP for glycolysis is 2 ATPs. So here's our glucose molecule. Here are 2 NAD molecules. We're going to require ADP molecules to be converted into ATP, and then that's going to give us 2 pyruvate, 2 NADH molecules, high energy molecules, 4 protons, and 2 water molecules. So this is the summary reaction of glycolysis that basically takes all the steps we just talked about and summarizes them in a very concise way. So this is glycolysis, the initial breakdown of glucose for energy. So the process of glycolysis is regulated. It's going to be regulated at the enzymes I mentioned. So hexokinase, if we have a lot of the product, glucose 6-phosphate present, that's going to turn off the hexokinase enzyme. So that's going to prevent the phosphorylation of glucose. If we've got a lot of the product, then we don't need to make more of that. So reaction 3 is the second major regulatory place for glycolysis, and that step is catalyzed by phosphofructokinase. So it's converting fructose 6-phosphate into fructose 1,6-bisphosphate. And this enzyme is really one that is taking all kinds of information into account when determining whether or not it needs to be activated. Remember that the overall point of breaking down glucose is to generate high energy molecules like ATP. So if there are already plenty of ATP molecules present, then this enzyme doesn't need to drive the process of creating more. So high levels of ATP will inhibit this enzyme, phosphofructokinase. On the flip side, if there are large amounts of ADP or AMP, this is an indication that the cell is being starved for high energy molecules. So high amounts of ADP or AMP will actually activate this enzyme. Now these little molecules, ATP and ADP, actually act directly on the enzyme itself in a process called allosteric regulation. That'll mean a little bit more later on. Pyruvate kinase, again, is the final or the third regulatory enzyme. And again, this one is going to be inhibited by high levels of ATP. So high levels of ATP indicate lots of energy is available, so there's no need to make more of those high energy molecules. The other molecule that plays into regulating pyruvate kinase is acetyl-CoA. Now that is going to be one step beyond the pyruvate product of glycolysis. This will make a bit more sense whenever we continue our discussion in the next couple of sections. So just for right now, know that the inhibition is going to be caused by products of the pathway. So the pathway produces ATP, so that's going to turn off pyruvate kinase. And then the product, one step beyond pyruvate, also turns off this enzyme. So these three enzymes are on-off switches for the overall pathway. So this is a table summarizing what I just talked about. So again, these are going to be the allosterically regulated enzymes that are either activated or inhibited by certain molecules in the cell. So work through understanding this, seeing how and why it makes sense that these molecules are either activating or inhibiting these enzymes. Because remember, the enzymes are driving the process of taking glucose molecules, breaking them down into smaller pieces so that we can capture energy in the form of molecules like ATP or NADH.